Alright, hello everybody. I hope you're all doing well. Just so you know that this is the second time that I've recorded this. I did it the first time on my computer and it crashed gloriously. So I'm doing this again on my school iPad using a method that I know will work because I've done it before. This video is to replace the class that was missed on February the 26th. Here you can see that I've slotted it to be done on March the 30th, but of course the beauty of asynchronous learning is that you can do it whenever you like at your own pace. Speaking of which, I'm going to be going a little bit faster than usual. This is with the knowledge that you can pause the video, that you can replay it, so don't freak out at that. Also, just know that this is going to be a little bit awkward for me. I've been doing a lot of videos for my high school students, doing like little solutions and that sort of thing, and it's been very awkward in how much I've been needing to listen to my own voice. So hopefully it's okay. All of us teachers are kind of diving into this whole online platform thing, and it's a pretty steep learning curve, so hopefully this will be palatable and not super painful. I'll try to be as fast as I can with it. I also have a pen, so that's one benefit of using the iPad. Okay, let's start off with a definition to define radioactive. So something that is radioactive will spontaneously emit radiation. So by radiation, I mean either particles or high energy photons. So something that's radioactive will essentially spit out other particles or little bundles of energy. So typically when we think about things that are radioactive, we think about nuclear fallout, we think about kind of pop culture things like, for example, you might think of the radioactive cats, you know, the art piece with those neon green cats from the 80s. It's definitely been embedded into popular culture that things that are radioactive are very dangerous. And I think in a lot of cases that's true, but it's not in every case. Just notice that we are subject to low levels of radiation every day, all the time. So just something to keep in mind, that radioactive radiation, there's a really large range of how harmful it is, which we'll talk about in a couple minutes. So that's what it means to be radioactive. I wanted to start off with a few other definitions as well, just so that we're all on the same page, and I'm going to start throwing some vocabulary around, and I want you to be ready. So if something is to decay, that means that it transforms into multiple other particles. So that could mean that the nucleus could eject some protons and neutrons and become another particle, or it could mean that it just kind of magically, if you will, transforms into other particles. And this is not actual magic. There is science behind it. It might seem like magic. So for example, we'll look at beta decay, which produces a proton, where a neutron produces a proton and an electron. You might think that kind of comes from nowhere, and the fact that it kind of does, it comes from fluctuations in the quantum field. However, that's beyond the scope of this course, so just trust me in that when you get on the quantum level, classical physics, so the physics that you deal with on a day-to-day basis, no longer always holds. Alright, so just trust me when I say that things can pop in and out of existence. Great. So a photon, by definition, you can think about it as a particle of light. It's a little bit more complicated than that, but for now, that's a good mental image. It transmits light, or it could transmit other, so light is an electromagnetic wave, so a photon could transmit other types of electromagnetic waves as well. So next I'm going to talk about 3 types of radiation. There are 3. The first one is alpha radiation. So for when something undergoes alpha decay, it will, from the nucleus, emit 2 protons and 2 neutrons. Now when that happens, the atomic number, or the number of protons, will go down by 2, and the atomic mass will go down by 4. So when it emits this 2 protons and 2 neutrons, you might notice, well, that's actually helium, right? That's helium-4. So helium-4 is also known as an alpha particle. So an alpha radiation is when a nucleus, by alpha decay, emits an alpha particle. So I'm going to show you an example in the next slide of what this sort of means for the initial particle. Typically we call the first particle, the one that we're starting from, the parent nucleus. And then the result after the decay, after the radiation, is produced, the daughter nucleus. So very familiar. Okay, so first example, what is produced when uranium-238 undergoes alpha decay? So we know the mass number of uranium-238, it's 238. We also know the atomic number of uranium, it's 92. I put a little screen capture of a chunk of the periodic table up here for reference so you don't have to scroll back. So we're going to write it as a chemical equation. Okay, so we're going to start with our initial uranium-238. So remember the notation for isotopes. Uranium-238 is the mass number. 92 is the atomic number. So, and U is the symbol for uranium. So when it decays, remember that for alpha decay, it loses 2 protons. So the atomic number will go down by 2. So if we look at uranium's here, 92, if we go down by 2 protons, we're now going to be at thorium. So by alpha decay, this uranium is going to transform into thorium. And the mass number is going to go down by 4. So here we go. Mass number 234, right? You subtract 4 from the initial. 92 is the number of protons. We've lost 2 protons in our alpha particle, so that number has gone down to 90. And finally, we know that when it goes down by 2, we have thorium, so we need to use the chemical symbol for thorium. Okay, so it emits thorium. And also we need to include the helium nucleus. So we can write helium-4, mass number 4, atomic number 2. And every alpha decay is going to act exactly like this. So let's see if you've understood. You can try it. What is produced when actinium-225 undergoes alpha decay? So take a little bit of time. I've screenshotted the relevant a chunk of the periodic table for you. Note that radioactive elements, so those are elements that have no stable isotope. So there are a lot of elements that are able to undergo radioactive behavior, but specifically radioactive elements mean that they are never stable. So no stable isotopes. On the periodic table, it's elements 84 to 118 if we're looking at the atomic number. There's a couple additional ones like 43. And yeah, so all of these elements have no stable isotopes once you get past 84. All right, have you tried it? Let's look at the answer. So actinium-225, we know the atomic number of actinium is here. It's 89. So when it undergoes alpha decay, the atomic number is going to go down by 2. When that happens, 89 becomes 87, and we have francium. So it becomes francium, and then we always have to put our helium. Do you get that? Great. It's very strange to not pause and ask for questions. I know this is online. Like, this is recorded, so obviously that's ridiculous. So what I want you to do is I want you to, if you have any questions that come up, write them down. I'm going to give you some opportunity in the future to be able to ask those questions. So just hang on to them for now. If they're really burning, you're welcome to email them to me. All right, second kind of radiation is beta. I'm going to be really paranoid and make sure, yeah, I'm still recording. Whew. Nice. Okay, so beta radiation is when a neutron in a nucleus decays into a proton and an electron. Okay, so know that this doesn't mean, I was alluding to this earlier, but this doesn't mean that there's a proton and an electron trapped inside every neutron waiting to be free. Due to fluctuations in this quantum field, this neutron will produce a proton and an electron. It actually also produces a third particle called a neutrino, but that's a very light particle. It interacts with things very, very weakly. You actually have trillions of them going through your body at every second from the sun, so solar neutrinos that happen with different chemical reactions that happen from the sun, from rays from the sun. So we don't, at this level, we don't need to include the neutrino. So just say for now, proton, electron. So beta radiation, try that, happens when you have an isotope that has a very large number of neutrons. So it has so many neutrons, it's, you can say that the element, it's not equipped to have so many neutrons. So something's got to give. They're unstable. So when that happens, they're likely to undergo a beta decay and produce a beta particle. The beta particle is also known as an electron. We just call it a fancy name because it takes part in beta radiation. Note it's also a high energy electron. So when the neutron decays into a proton and an electron, what's going to happen to the element? Well, since we have a neutron changing into a proton, the mass number is going to stay the same, right? Since a neutron and a proton is about the same mass. However, we have one extra proton, so the atomic number is going to increase by 1. So you do have the result, the result will still be a different particle, a different element. Let's look at an example. What is produced when carbon-14 undergoes beta decay? So beta decay, so we're spinning out a proton and an electron. So let's start with carbon-14. Atomic number of carbon is 6, always. So you start here. The atomic number is going to go up by 1. We can see the carbon is then going to become nitrogen. So nitrogen 14, because the atomic number is not going to change. The mass number is not going to change. The atomic number increases by 1. And then you also include the electron that's added on. So let's give you the chance to try what's produced when iron-52 undergoes beta decay. So take a second and try that. Okay, Okay, so iron, 52, the atomic number is 26. All right, it's right here. When it undergoes beta decay, the atomic number increases by 1. So increases by 1, we're going to end up with cobalt with atomic number 27. Mass number is going to be the same, and then you add an electron, always. So that's all beta decays. That's all you need to know how to do. The last type of radiation is gamma radiation. So gamma radiation happens when there is either an alpha or a beta decay. It kind of goes alongside. And it's when there is an emission of a high energy photon. Okay, that's better known in this case as a gamma particle. So it emits all these different gamma particles. It's essentially emitting energy. Okay, so the effect that this has, it doesn't have an effect on the actual elements that are involved. It doesn't change the radioactive element into a different radioactive element, but it's just important to note that this type of radiation is occurring. So here's the reaction, the decay of uranium that we saw earlier. It's turning into thorium and helium, but note that even in this reaction, there's also going to be some high energy photons that are released as well. They show up here. So you won't need to know how many photons are released. That's kind of, that's pretty advanced stuff, but just know that just kind of the definition of gamma radiation is when gamma particles or high energy photons are released. So when does radiation become dangerous? I already said that not all radiation is necessarily dangerous. So let's look at radiation dosage. So for humans, there's a few units that we use. One is grays, GY. Another is rads, so radiation absorbed dose. So the definition of a rad is 0.01 joules per kilogram. And the types of radiation have different conversions to rads. We're not going to go into detail about this. There's a little bit more detail in your book if you want to look at it. But in order to take this into account, so I mean, you can imagine, I think one analogy that they use in the book is that alpha radiation is kind of like little arrows, and beta radiation is like arrows but with suction cups on the end, right? You could have the same number of arrows, but the impact of those are going to be quite different. So to take that into account, you can convert them to rems, which is Röntgen equivalent man. I don't know who came up with that, but those units are often used because it kind of levels the playing field, if you will. It just tells you how much radiation would you need for there to be some harm done. So, for example, 1 rad of alpha particles is going to give the same amount of radiation as 10 rads of beta particles. So obviously the alpha particles are stronger because it takes 10 of them to be able to do the same amount of damage with beta particles, with beta radiation. So on a day-to-day, we all have some exposure to radiation, even say living in a stone house or being around stone, right? Metals often give off some radiation. There's radiation in the air, the radiation from the sun. There's radiation from the ground and from the elements in the ground. The TV emits radiation. Probably one of the first things you might think of would be medical procedures. So of course, CT scans emit radiation and different other procedures, x-rays. And also we might be exposed to a small amount of residue from nuclear fallout that's still in the air. So overall, we do need to be careful that we're not exposing ourselves to too much radiation. The radiation from, say, the TV or from the air, cells are really good at repairing themselves and looking after themselves, so they are able to pretty easily withstand the radiation that comes from those sources. If you have radiation from a lot of intensive medical procedures, then the cells are not as good at of fixing themselves from that, and sometimes they can't. So obviously, exposure to radiation is something, we have to kind of keep in our minds, right? It's a little bit common sense, but that's just putting a few numbers into it. This table is interesting, looking at how severe the different sources of radiation can be. All right, the next thing I want to talk about is the decay rate. So using by alpha decay or beta decay, elements will become other elements. So the half-life is how we talk about how fast this happens. So the half-life is how much time it takes for half of an original sample to decay to other elements. So it's the amount of time that the original sample that you have has decreased by half. So half of it has decayed to other elements. Okay, so we've lost half of it. The amount of time that takes is called the half-life, and that's something that's pretty consistent, pretty stable for given isotopes. So it's something we can calculate, it's something we can predict. Of course, there's some variation if we're looking at individual particles, but that's kind of the big average is what we call the half-life. So an example of using the half-life, so say I say that the half-life of uranium-232 is 70 years. And say I had an 80-gram sample of uranium. That would be hard. Uranium is pretty rare. So I have 80 grams of uranium. Since my half-life is 70 years, it's going to take me about 70 years for there to be 40 grams of my sample remaining. After 140 years, half of that is going to be remaining. So you can just multiply the 40 by 1/2, and you get 20. After another 70 years, half of that amount is going to be left. So we multiply the 20 by 1/2, we get 10 grams left. After another 70 years, we're going to have another half of that sample left. So we multiply 10 by 1/2, and you get 5 grams. So, of course, going from one half-life to the next, you're just multiplying by a factor of 1/2. And you can do that indefinitely. All right, another example, an isotope has a half-life of 6 hours. How long will it take for a 60-gram sample to decay to 15 grams? So since the half-life is 6 hours, I know that after 6 hours, I only have 30 grams left. I've lost half of it. After another 6 hours, I've lost half of that. So I've lost half of 30, which is 15 grams. So after 12 hours, I have 15 grams remaining. So that answers my question. It says it wants to decay. How long does it take to decay to 15 grams? It will take 12 hours. Okay? Does that make sense? Again, I know that you can't answer. So if you need help with this, let me know. If you're taking math, you might have also seen an equation for this. It's an exponential. Have an exponential curve. It looks something like that. If you want, it'd be very easy, if you've seen this, to be able to set up an equation for this. But there's no need. We can just do it manually. I won't give you anything too crazy. All right, so let's ignore this. I should have put a transition in it, but I didn't. So anyway, if the half-life of radium-224 is 3.66 days, how much of a 120 gram sample will be left after 14.64 days? So give that a try. Pause this. Don't look at what's under the red. That's the answer. Pause it. Give it a look. I'll see if I can erase this. Oops. Not zoom in. Maybe I can't. Maybe I can't. Oh, that's unfortunate. I can just flip forward. Oops. Now I've exited out from current. There. Try again. Alright, so hopefully you've taken the time to do the problem. So since the half-life is 3.66 days, after 3.66 days, I know I have half of my original sample, so I'll have 60 now. After another half-life, so 7.32 days from the start, I'm going to have half of that, so I'm going to have half of 60, which is 30. After 10.98 days, I'm going to have half of 30, which is 15. And after one more half-life, after 14.63 days, 64 days, I'm going to have half of 15, which is 7.5 grams. So my final answer is 7.5. I want you to note that, so when something decays, often the products of that decay will also decay, and that will make a kind of a decay chain. So we can't just look for like half-life. You can't say just look of, say, uranium. You can't just look at how much thorium you have after so long, because the thorium's also going to decay to protactinium, which will decay to actinium, and so on, by different decay routes. So just note that that the products of decay will also decay. And it's very interesting, the half-lives are illustrated, and notice you have some on the scale of years, like it's a huge number of years. Uranium-235 to francium-223 here. The half-life of that is 22 minutes. Look, here's even better. Half-life of thallium, is 4.77 minutes. So it's very, here's one, what's this? Oh gosh, this is in seconds. Ooh, so is this. Okay, so there are some very low numbers in this, very, very low half-life. So the rate of decay is very, very high. The very last thing I want to talk to you today is about radiocarbon dating. If you do have a lab on it, I'm going to figure out how to do that lab. If you have access to the technology, it's something that you can do online. So we'll figure that out. I'll be in touch. So in a nutshell, quick overview, and maybe it feels like an overload. Quick overview, since we'll go into a little bit more detail in the lab, is that radiocarbon dating is how we can use artifacts, so things that we've discovered or dug up, and we use them to find, we can do it. Gosh, what am I saying? You can do an analysis on this organic matter to determine how old it is. Okay, so you can do this using the amount of carbon-12 that's found in the organic matter, and also the amount of carbon-14. So carbon-14 is special. Carbon-14 is created in the upper atmosphere when cosmic rays hit nitrogen. And when that happens, it changes the nitrogen into carbon. So carbon-14 is fairly unstable. So you could say that it's radioactive, right? So this carbon-14 then, comes down to Earth, and it is used, it's consumed, it's integrated into the supply of carbon that we use. Often it connects with oxygen and it's formed into CO2. So when that happens, it's not likely to decay when it's in a bond with oxygen. So it's kind of locked into that. So it just behaves exactly as regular carbon would. So once something dies, this carbon-14 will start to lose its oxygen. And when that happens, it's going to become free to decay back into nitrogen. So the half-life of this, so about half the carbon-14 will be gone after about 5,730 years. So in all of this, the amount of carbon-12 is going to be pretty stable. It stays constant. But the carbon-14 level will decrease. And of course, there are a lot of other factors that you have to take into account when doing this. You have to take into account the type of creature, its environment, its what it eats, its elevation, right? All these different things can affect the amount of carbon-14 that it has. But once you know all of those factors, you can use that comparison to the amount of carbon-12 to determine how old it is. So very, very, very neat technology to be able to do that. So again, any questions, write them down. We'll have, a question answer, something in the near future. Hopefully this wasn't too long or unbearable. I hope you all very much are doing well and are hanging in there and staying sane. Please don't hesitate to reach out if you need anything from me. All right, let's stop this. Have a good one.